Our next team two, they're coming in. The Logan's Legends will be represented by Vicky Trichard from the NRCan GSC. And the title is Dismantling Geosilos, an integrated model for copper porphyry prospectivity in the Quesnel terrain of BC.
Okay, so let's forward, back, and
Is there a laser pointer?
there.
Perfect.
And that
Okay.
butter's fresh, and I'll keep it there.
Okay. Hi, I'm Vicky, and I'm with the Geological Survey of Canada, and our team includes people who have or formerly worked at the Geological Survey of Canada. We originally picked our team to include people working there that had less than 5 years experience, which included myself, a geophysicist, my brother, also a geophysicist, a 3D modeler, a structural geologist, and two geochemists. So when we started this project, one of the first things we did when trying to figure out where do we go from here is we did a series of Science 101 talks where we had sessions with each other to outline what our specific scientific disciplines could bring to the table, to familiarize each other with the geochemistry, which I was completely unfamiliar with before beginning this. The geochemists got to see what I did as a geophysicist, and then working together to see what linkages we could find between the disparate geoscientific disciplines. And then as well, this really helped to open the lines of communication between us. So this ended up having monthly to bi-weekly meetings in person to discuss the findings as we were working toward it and to set short-term goals, as well as having weekly email correspondence to work on the data integration and to discuss what we had found out. So we entered the competition for the Quesnel terrain because it's one of the world's most diverse and comprehensive data sets, and it gave us a lot of opportunity to integrate multiple public data sets to add value to Canada, which is a benefit to the Geological Survey of Canada, as Donna mentioned, and to stakeholders operating in the area. As well, it played the data sets available in the region played to our disciplines. There was something for all of us to work with. And as well, none of us had worked on a copper porphyry system before. We all had experience in different deposit types. So it gave us an opportunity to learn something new, as well as giving us a time to develop new methods for exploration and visualization in areas covered by glacial overburden, which can be a bit of an issue in Canada. So the Quesnel terrain in British Columbia hosts several world-class porphyry, copper gold, and copper molybdenum deposits, but none of them have been discovered in the area in the center where there's quaternary cover, so there's a lot of potential for undiscovered deposits. So ultimately the goal of our work was to identify new targets in this covered areas by looking at multiple geoscientific vectors. So did these till-covered deposits have a geochemical expression that could be correlated to both geological and geophysical lines of evidence? So the data we used to solve this were quaternary sediment geochemical data sets, which will reflect the properties of the surface material that's been transported from the bedrock source. Geophysical data sets that are the subsurface and reflect the physical properties. So for gravity, you're looking for density variations, magnetic susceptibility variations, and then EM conductivity. And the structural data sets, so reflecting the structural history of the area, the geological setting, and the ore system itself. And all the data we used in this analysis were publicly available through the GSC, the British Columbia Geological Survey, or Geoscience BC. So the stream and lake sediment data we used was provided by Geoscience BC and includes over 30 years of data. And the distribution of these elements are useful as proxies for looking at the bedrock geology as well as for the mineralization. So we culled the geochemical or the element list to 34 elements, and these were leveled against each other to have the best geographic coverage, as well as doing QA/QC to ensure the data was reproducible and comparable within the region we were looking at. From here, we did a neural network analysis to infer the predicted geology, which was then weighted based on the prospectivity of those rocks to host deposits. So, for example, the red are the most prospective on the map, and these are early to mid-Proterozoic rocks that are prospective for alkalic copper gold mineralization in the south, whereas, for example, the 0.25 prospectivity, the Nikola and Tekla volcanics, were not prospective at all for copper porphyry, but they would have provided a barrier or a chamber to channel the magma, so that's more of a structural feature that would be important. And then from the data sets, we did principal component analysis to look for copper porphyry signals. So on the map, we had prospective rocks at Mount Milligan, but we also had a second cluster to the south that hadn't been looked at before. The third geochemical technique we used is conditional probability. So we used proxies from the MD mineralized data set for copper porphyry mineralization, including the data from and around Mount Milligan and Mount Poly, to get a kernel density estimation. So the bigger the kernel density estimation, the more potential for mineralization. The one limitation with this approach is that the mineralized data set is much smaller than the TD total data set. So we did a joint relative probability instead of, so we assigned weights to 3 specific ratios that were the most prospective for copper or porphyry mineralization, the CU, CD, CU, MO, and SRK, and then summed the posterior probabilities to get the joint relative probability, which the most prospective samples were arbitrarily assigned a value of greater than 0.8, and this was to reduce clutter on the map and are shown on the figure in red. And we just want to point out that the area to the southeast, that looks like a cluster on the map and that it would be prospective, but that's related to the lithology, not to the mineralization potential. It's on an area of volcanic rocks that aren't prospective. The next step was taking a step back and looking at the geology. So there had been some work done in the south that identified a series of belts that transect the area, and presumably the surface trace of these belts could be extracted or extrapolated below the covered area. So our structural geologists looked at all the dating that had been done for the rocks and anything available and reconstructed the surface trace of these belts. And as well, from the south, plutonic centers, which is where these copper porphyry deposits are located, are generally at a characteristic spacing. So we looked at the deposits to the south and to the north and figured out what that spacing is, and then interpret it below the quaternary sediments. And as well, there was a paper from 2015 through the Quest data that provided a beautiful geological geophysical integration of the area. So we were able to get some structures from that. So the pre-Ticine tectonic faults would have channeled magmas and fluids and would be prospective. So these are the north-south faults shown in gray on the map, as well as cross-arc structures that would have been at a low angle to the major stress direction and would have been prime sites for magma and fluid transport and then hosting mineralization. So these are the northwest, southeast gray lines on the map. Geophysically, there was gravity, magnetic, and conductivity maps available through the area. So a lot of the copper showings were on gravity highs or at the edges of gravity lows. And this is related to the regionally prospective geological features, such as large intrusions. On the magnetic map, many of the copper showings were on mag highs, so batholiths or volcanic flows, and this was also because it's a higher resolution, was really good for helping to interpret the structure. On the conductivity map, a lot of the early channels show conductive overburden, but a lot of the porphyries root systems showed an area of deep conductance. And we also had a look at any IP effects in the conductivity or in the EM data to see if they were there, because there had been IP effects associated with Mount Milliken. We looked at the long line data to see if there was negative transients, and then sum these together. So to bring things together in 3D, we did a worming of gravity and magnetic data sets to estimate the dip in geometry. So worming works by when you upward continue a source edge geophysical data set, the maxima will migrate in the down dip direction, so you can get an idea of which way it's presumably dipping in a perfect world. And it can be roughly correlated to the depth of this maxima is at approximately half the upward continuation distance. As well, we contacted the British Columbia Geological Survey and asked them for their structural database, which we digitized. And then taking the style dip and dip direction from the north and south where things are exposed and extrapolating it, and then interpolating surfaces using the worming information, we were able to construct 3D surfaces, which helped with the visualization of the fault intersections and how they related to the geophysical features at depth. So taking all these proxies into account and then assigning weights based on their potential to host mineralization, we built together a prospectivity map. So the characteristics from each proxy, which I just mentioned, were assigned a weight based on how prospective they would be. So if this specific feature would more likely to be prospective for copper porphyry mineralization, and then built using a series of knowledge-driven, so these are the interpretations, and data-driven, so the geophysical maps results, and then weighting the sum. And then we used the lake and stream sediment geochemistry for validation. And the figure to the right shows the prospectivity map we constructed for the area with the geochemical anomaly shown in red and green. And the circles are the plutonic centers that we interpreted from the data. To display everything in 3D, we used a geoscience analyst because part of the rubric for the competition was trying to use as much free software as possible, and Geoscience Analyst was free, and it's 3D, which was also part of the rubric. And it allowed us to import and display a lot of different data sets, so it was able to handle all my geophysical data sets, but also the 3D modeling stuff was able to work good in the geochemistry data sets and the geology, the shape files. So by overlaying all this stuff together in 3D, we were able to turn stuff on and off to get an idea of how things were relating to each other and to start seeing relationships between the disparate data sets and identify potential targets in a 3D framework. So we identified 3 copper porphyry targets, which are the red circles on the prospectivity map, and then we validated these targets looking at the principal component analysis data and the conditional probability points. So Mount Milliken is an anomaly on the map and would be considered a prospective area, but because our geochemical data sets and structural data sets were trained against this area, it's kind of a self-fulfilling prophecy. But talking to the geochemists, they didn't touch Chuchi Lake as a part of in training their data sets to look for the mineralized targets, and that shows up quite nicely on the prospectivity map and stands out a bit more than our target 1, target 2, target 3, just because there are more showings there, and as well it's not covered by overburden, so the geophysical expression is much more pronounced. So I'm just going to go through our 3 targets and kind of why we picked them. So the first one is located in the north and contains the intersecting cross-arc structures that we care about. It was located over a neural network inferred pluton, as well as one of our interpreted plutonic centers. And then we have the co-located geophysical anomalies, suggesting that there's a buried intrusive body at depth. And as well, there were prospective conditional probability and principal component analysis that were down ice from the glacial transport direction in vicinity of our target area. Target 2 is in the center of the area and is covered by 2 kilometers of overburden, so it's quite buried. And it corresponded to the, again, intersecting cross-arc structures that are near an interpreted plutonic center and a magnetic high. It's validated by the co-located prospective conditional probability sample, and the one on a long line on the EM data, there was a large negative transient that couldn't be correlated to any anthropogenic sources. Target 3 had a co-located gravity magnetic and EM anomaly, suggesting another buried intrusive body. And this area to the south, one of the reasons we didn't look at the radiometric maps is because they weren't over the overburden area, but this target also had a potassium anomaly, so we related it to potential potassic alteration, as well as intersecting cross-section structures that are again near an interpreted plutonic center. So one of the things I forgot to mention is with the geophysical data sets, it also came with 3D inversion volumes, which helped with our visualization in 3D by being able to construct isosurfaces. So these are target 2 and target 3, and the green circle is the interpreted plutonic surface or center that's been draped to the topography, which is why it's bendy, as well as the inversion isosurface shown in yellow, and then the worming maxima shown in red. And they all work really nicely together. The plutonic center is close to this body at depth, and the worming geometry of the source is very similar to the inversion volume of the source, which was unconstrained, so there's a lot of leeway in what it could be. So the innovative outcomes of our work were that we identified 3 targets in the covered area of the Quesnel terrain, and by doing so, we developed a 3D workflow to integrate these different kinds of data sets, and using the geophysical data sets to see undercover, and then relating it to the superficial geochemical data sets and looking for linkages between the two. We used the conditional probability for the geochemical exploration using legacy data, so making use of old data sets, bringing it together and modernizing it so it's a contiguous data set, and then doing target visualization in the covered area, so integrating the geology with the geophysics, with the structural data to build a 3D fault network. So our work represents the most inclusive geophysical, geochemical, and geological data integration and interpretation of the Quesnel that's been done to date, and we also generated the prospectivity map that includes the 10 exploration criteria and a 3D model for the area. So our method has value for deep and covered areas, which is commonly what's found in Canada, and this is the kind of stuff as the Geological Survey we're going to have to be dealing with. And it provides a way for vectoring and selecting targets using a lot of free and standard use software, so there's minimal financial impact on the companies that are exploring. And because we're the government and we like to make the most of our public data, this provides a great case study of showing how to make the most out of your public data sets. So we were looking for regionally prospective areas to inform the boots on the ground targeting that would follow up later. So we want to thank Eric, who was our 3D modeling mentor, but then several others at the GSC and various government surveys that provided guidance and mentor. And one of the results from the work we've done here are going to be part of the Canada in 3D program, and we'll feed into that with the goal of having Canada in 3D eventually, which will feed into the open science mandate at the Geological Survey.